All right, let's look at another differential equation exercise. So this one's a little different because it's not about a falling object. This is about an object moving on a straight line. In fact, two objects moving on a straight line. We have two cars, or a car and a truck, moving on a straight line, parallel to each other. Um, and let's just see what the example says. At the moment a traffic light turns green, a car begins to move forward with a constant acceleration of 6 feet per second. Okay, so let's see here. I get a traffic light and it starts to move forward at a rate of 6 feet, sorry, at an acceleration of 6 feet per second. So we can say A of t is 6 feet per second squared. Okay, this is the car. At the same moment, a truck passes by the car with a constant velocity of 60 feet per second. Okay, so you have a car and a truck. They're briefly right beside each other at the moment where the red light turns to green. So I guess I guess the only way for this to happen would be if that truck was either really had some really good intuition and knew that light was about to turn green, or that truck was about to run the red light, because it's going at 60 feet per second, no plan to stop. And it just so happens the light turns green. Okay, so the car is stopped, but starts going at a constant acceleration, but the truck has a constant velocity of 60 feet per second. Okay, now let's see what we're trying to figure out here. How long will it take for the car to overtake the truck? How far away from the traffic light will the car overtake the truck? What will the speed of the car be at this point? So, a couple observations here. We're trying to figure out when the car overtakes the truck, and we're concerned about the distance away from the traffic light. So, the traffic light can be thought of as our initial position. That's your starting point. And we want to know how far away from the traffic light will the car overtake the truck, because the car is accelerating, at 6 feet per second, then 12 feet per second, then at 18 feet per second, then at 24 feet per second. So every second, it's going 6 seconds faster. I mean, six feet per second faster. That's what it means for you acceleration. You're at zero. You're at 0 meters per second. Sorry, feet per second. At time 1, you're moving at 6 feet per second. At time 2, you're moving at 12 feet per second. At time 3, at 18. At time 4, 24. So eventually, it's going to be going really fast. And it's going to overtake that truck that's traveling 60 feet per second. Because think about it. At time 10 seconds, the car will be going 60 miles per hour. Now, the truck will be long gone. But then at time 11, it'll be going 66 miles per hour. At time 12, it'll be going 72 miles per hour. Meanwhile, the truck is still going 60. Sorry, I said 60 miles. 60 feet per second. Sorry. Meanwhile, the truck is going 60 feet per second. Okay, so let's see what we can do. So we're trying to find whether positions are equal. Well, that means we need to find the position function of each car, of the car of the truck, and then set those equal to each other. So let's work with the truck first. I think that's a little easier. We know the truck has a constant velocity of 60 feet per second. Well, it's easy to get position function because remember, the antiderivative of velocity is position. So the position function of the truck is going to be the antiderivative of the velocity function, which is the antiderivative of 60 dt. Okay, which that's pretty easy to do, right? It's just a constant, so 60t plus c. Now we need to figure out what c is. Now remember, c is the initial position in this case because you're talking about the position function now. C would be the initial position, but we know that we're talking about the moment the car and the truck were right at the stoplight at the same moment when the stoplight turned green. So that tells me that that S of 0 equals 0. That is the position of the truck was at the stoplight at time 0. So we know that S of 0, so here's my tentative solution, but S of 0 equals 0 implies that 60 times 0 plus C has to equal 0, which only has the solution, C equals 0. So the final position function of the truck is simply going to be S of t equals 60t. Position of the truck. Now, let's do the same thing for the car, except the car, we don't know the velocity of the car, we know the acceleration. So we have to do a little more work for the car because we are starting with A of t is 6 feet per second. Okay, but we can get the velocity because we know that the velocity function is the antiderivative of the acceleration function. Which of course is the antiderivative of 6 dt. Okay, that's a constant, and so it's just 6t plus c. But what is the initial velocity of the car? We know the car is sitting still because it says at the moment the traffic light turns green, a car begins to move. So that implies that it was staying still. In other words, that the initial velocity was 0. So we could say, but, so this is my tentative solution for my velocity function, but v of 0 equals 0 implies, that 6 times 0 plus c has to equal 0, which again implies c equals 0. So my final velocity function of the car is v of t equals 6t. Velocity of the car. And now let's find the position of the car. So the position of the car, S of t, is the antiderivative of the velocity of the car. And the velocity of the car is 6t dt, which tells us, according to the power rule of antidifferentiation, that at least the tentative position function is going to be 6t squared over 2 plus c. Of course, if we simplify this a little bit, that's 3t squared plus c. Okay, but what is the initial position of the car? Well, just like the car and the truck were underneath the stoplight at the moment it turned green. And the position we're measuring is the distance away from the stoplight. So that tells us that S of 0 equals 0 also for the car, which implies that 3 times 0 squared plus c has to equal 0, which of course implies that c equals 0. So the final position function of the car is just going to be 3t squared. Now, we want to know where the positions are equal. So we quite literally equate the position functions. So let's see, position of the car equals position of the truck. And what? That's going to be what? 3t squared equals 60t. That's a quadratic, so we can set it equal to 0 to solve. 3t squared minus 60t equals 0. Okay, that can be easily factored. Factor a 3t out. That leaves us with t minus 20 equals 0, and that has the two solutions. The first solution is t equals 0, or t minus 20 equals 0, which implies that t equals 20 seconds, of course. Now, why does that t equals 0 make sense? Because we know that at the moment where the stoplight turns green, the car and the truck are right beside each other. So at time equals 0, yes, their positions are equal. And then again, at time equal 20 seconds, they're equal. That's when the car overtakes the truck. So at 20 seconds, now how far away from the traffic light are we at that point? So the distance from the light, well, we can use either of our position functions because we know that the positions are equal at time equals 20 seconds. So I guess we could, this is the easier one, right? 60t, so what's 60 times 20? 6 times 2 is 12, add a couple zeros. So S of, 20 is 60 times 20. I'm using the truck position function, equals 1,200 feet. Okay? And then what is the speed of the car? Well, what's the speed? We need to go to the velocity function of the car. So that's a v of 20 seconds. And the velocity was 6 times t, so 6 times 20 equals 120 feet per second. So it takes 20 seconds for the car to overtake the truck. At that point, both the car and the truck are 1,200 feet away from the stoplight, from the starting point, and the car is going 120 feet per second. Okay? By the way, like I mentioned this in passing, but the distance from the light, you could also plug into the position function from the car. Notice that if you plug in 20 into 3 times 20 squared, you get 1,200 also. So you could use the position function of either. I just used the one that was linear since that's a little easier. Okay? So again, I think that's a very interesting exercise. We could use what we know about antiderivatives and velocity and position and how those things are related to solve this rectilinear motion problem. So we'll do a couple more of these. As always, if you have any questions, always feel free to reach out. Always more than happy to help you. I'll catch you in the next video.